We're going to use the color of sheep's wool for the next few examples to show the basics of Punnett squares and Mendelian law. White wool is going to be our dominant trait, and black wool is going to be our recessive trait. We will represent white wool with a capital W and black wool with a lowercase w. If we were to mate a white-wooled sheep who had a parent that had black wool with a black-wooled sheep, then what could their offspring be? First, we need to figure out what the genotype of the white-wooled sheep could be if they had a parent with black wool. Because we know that one of her parents had black wool, then she is going to have one of the recessive traits for black wool of little w. But because we see that she has white wool, we know that she has to have the dominant trait as well. So we can tell that our sheep is going to have the genotype of big W, little w. If we cross our original heterozygous white sheep with a homozygous recessive black sheep, we can figure out the Punnett square like this. We know that our white sheep can give two different kinds of eggs. One possibility would be a big W and the other is a little w. Our male sheep only has one possible kind of sperm to give, and that would be the recessive trait of little w. By filling in our Punnett square, we can see that our white female sheep could give some of the offspring of the dominant trait and some of the offspring the recessive trait, whereas our black male sheep can only give the recessive trait. By looking at this Punnett square, we can tell that 50% of their offspring could have white wool and could be heterozygous, whereas the other 50% could have black wool. Now, let's look at sex determination and look at specifically which sex chromosomes the male and female sheep could give to their offspring. So, male sheep are going to have two sex chromosomes, and will have both an X and a Y sex chromosome that it can give. Whereas our female sheep, which we have chosen to be white, has two sex chromosomes as well, but they're both X and X. Once again, we'll make a Punnett square to determine what genders their offspring could be. We will start with our white female sheep, because female sheep only have an X chromosome that they can give. The only eggs that they could give to their children are X chromosome eggs. In the male sheep, which we have previously determined to be our black sheep, they have two different sex chromosomes, and so there is the possibility of either giving an X sperm or a Y sperm to their offspring. Take a second and see if you can fill out the Punnett square, and then determine the probability of them having a boy or a girl. So hopefully your Punnett square has ended up looking a little bit something like this. From this table, we're able to calculate the probability of having a boy or having a girl. In this case, it would look like that we could have a chance of 50% of getting a boy and also a 50% chance of getting a girl. When faced with a genetics problem that complies with the Mendelian laws, you can always make a Punnett square to organize the information given and then figure out what your outcomes could be.
Now we're going to look at a slightly harder problem. In humans, curly hair is a dominant trait to straight hair. We will use the big H to denote the allele of curly hair, and the little h to denote an allele of straight hair for the next couple of problems. Let's look at this question. If a woman named Jane has curly hair, but her mother does not have curly hair and her father does have curly hair, and Jane mates with a man named Phil, who does not have curly hair, what genotypes and phenotypes would we expect in their offspring? In order to answer this question, we need to break it down into smaller pieces. First, let's try to find out what Jane's genotype is. Let's get this question out of the way here, and let's look at Jane's parents. So here's Jane's father and mother, and that's Jane. So we know that Jane's mother does not have curly hair, meaning her alleles must be little h, little h. So we'll put those up there with her. And her father, on the other hand, does have curly hair, which means his alleles are either big H, or big H, little h. So in this problem, it doesn't really matter what her father is. But we do know that Jane has curly hair, so she needs to have at least one big H, which will come from her father, and a little h, which we know will come from her mother, because that's the only thing that her mother can give. So this gives us Jane's genotype, which is heterozygous for curly hair, big H, little h. It's a little easier to predict Phil's genotype. Because he does not have curly hair, we know that he must be homozygous recessive, which means little h, little h. To find out what to expect in the genotype and phenotype of their offspring, we just need to do a simple cross. Because we know that Jane is heterozygous and Phil is homozygous recessive, we can tell exactly what alleles they'll contribute. So 50% of the time, Jane's egg is going to produce the big H allele. And the other 50%, she's going to contribute the little h. Whereas Phil has only the recessive allele, so he'll contribute the little h for all of his children. So this is what the different genotypes, possibilities of genotypes look like in each of the children. So from doing this cross, we learn that half of their children, or 50% chance of their children, will be big H, little h, heterozygous, and that there's a 50% chance that their children will be little h, homozygous recessive. So that means theoretically half of their children would have curly hair, half of their children would have straight hair. And that's what's understood as the phenotype, is what we actually see, the curly or straight hair. So now let's add a little drama to the story. Because Jane can't stand Phil's straight hair and wants a better chance of her children having curly hair, Jane and Phil get a divorce. Jane remarries another waving man with curly hair named Jamal. So now let's talk about the probability that Jane and Jamal's first child does not have curly hair. So let's look at the genotypes of both Jane and Jamal. So we know that Jane's genotype stays the same, heterozygous, and we know that Jamal has curly hair, but we don't know his genotype. So he has one of two possibilities, either homozygous dominant, big H, or heterozygous. To find the probability that their first child does not have curly hair, we need to do two crosses this time. We cannot just assume that Jamal's genotype is one or the other. So our two crosses look like this. One where Jamal is heterozygous, and one where he is homozygous dominant. The result of these crosses will appear as follows. So the question asks for the probability that Jane and Jamal's child will have straight hair, which means homozygous recessive. So what we're looking for is the probability of two small h's. Another way to do this would be to count the boxes. We can see each of the boxes here, 1, 2, 3, 4, 5, 6, 7, 8, and only one out of those 8 is that homozygous recessive gene for straight hair. So the answer to the question, what is the probability that their first child will have straight hair, is 1/8 probability. Now let's look at a new question. If your mother has dimples, an autosomal dominant trait, what is the probability that you will get the trait? Assume that your mother's mother has no dimples, and assume that your father has no dimples. So if your mother has dimples, we know that she has at least one big dominant D for dimples. We also know that her mother had no dimples, which implies that she is little d, so your mom must have one big D allele and one little d allele. We also know that your father does not have dimples, so that means he must be homozygous recessive, which is little d. So for the first part of this question, we need to do a cross between your mother's genotype and your father's genotype. In order to do that, we need to do a Punnett Square. Go ahead and pause the video and take some time to see if you can do that Punnett Square on your own, and then I'll show you what it looks like. Your Punnett Square should look something like this. So we can see here that there's a 50% chance that you will have dimples and a 50% chance that you'll have no dimples. Let's move on to the second part of the question. What is the probability that your child will have dimples if you marry a homozygous recessive individual? Once again, to answer this question, we'll need to do 2 crosses because we don't know what your genotype is. Go ahead and pause this video to take a minute to do the 2 different crosses, 2 different Punnett squares for possible genotypes. Your crosses should look something like this. So if you are homozygous recessive, there's a 0% chance that you'll have a child with dimples. Whereas if you're heterozygous, there's a 50% chance that your child will have dimples. So to find the complete probability of having a child with dimples, to calculate this, we need to calculate the total number of options, 1, 2, 3, 4, 5, 6, 7, 8. And we see that 2 of those 8 have dimples. Or in other words, there's a 25% chance of having dimples. The next part to this question, the homework, is very similar. It just changes the word homozygous to heterozygous. So what is the probability that your child will have dimples if you marry a heterozygous individual? So in order to calculate this, we just answer the exact same way we did the previous question. So I'll let you do that on your own. Good luck.